This is remotely. It's Linux again.
Yeah, I know. Let's hope for the best. Might take some time to disappear. Okay, good. I hope we have solved all the technical details. Seems to be small groups, so if you have any questions, we can discuss them in length, I guess. Topic of this session is extremes, which kind of we seen also yesterday in the talk of Martin Schulz, and which we're going to discuss a bit further today. Some of the work kind of goes back to my PhD time, but kind of extremes, I guess, still very relevant here to look at and to jump into. We have a few mathematical details in between, possibly due to my background. I originally studied mathematics and then did my PhD in geoinformatics at the Institute for Geoinformatics with ETSE. So kind of quick overview. We start kind of the univariate case when we have one random variable and looking into extremes in one dimension and discuss that. And then we start looking to multivariate extremes. So what's kind of the new problems that we have to tackle and to solve if we have more dimensions. And then later we introduce copulars and also look into copulars and how they can help to model spatial extremes. And then later we'll have time for a hands-on session. I have kind of few demos that you could look into and a few explanations. So that I guess kind of half of the time we spend kind of me talking, and the other half of the time you can also try a few things on your own machine, and I can kind of try to help you out where necessary. So really kind of a hands-on session. Okay, good. So let's start with the first block, the univariate extremes that we look at. Just kind of, so what's special about extremes? Rare events or measurements, typically just a few records in a spatial distributed scene, or just kind of a few records in the time series, or both, if you have spatial temporal data. So by definition, we will only have always just few extremes, if any at all, in a distribution that potentially can have extremes. So that's kind of the underlying modeling problem, that we kind of would like to model something that we just see very seldom, and that we have to use some theory in the background to kind of support this and kind of to build models that are designed and developed based on their mathematical concepts and basics to support this extreme value theory. And the extreme value theory is a whole branch of mathematics discussing and working on these problems and developing different distributions, different approaches, different estimation approaches, goodness of fit approaches to work with this use case of extremes, so that we can, even if we have just few data, kind of put some model assumptions on top, start to make some more or less sensible estimates on the kinds of extremes we have to expect. Yeah.
I have a question. Do you have any estimation of how many rare events can there be? So for the assumptions to hold, it's 10% of data, or even up to 10%, or much less.
Well, it can be quite few, but kind of for the estimation phase, there's kind of the rule of thumb. You need kind of 100 observations still per dimension that you would like to estimate. So it's very kind of challenging to get these together most of the time. So there's no.
Can you remove that bar from Zoom, or just move it at the bottom because we can't read? I think we know you can hide it. No. If you can just move it at the bottom of this, so we.
Okay, this works. Yeah.
Something like that.
And even.
Yes.
I'm afraid at some point we will need it again for whatever reason, but still there. Okay. Sorry. So let's look at an example of a univariate, now kind of extreme value distribution that I used here to kind of draw random numbers from the generalized extreme value distribution, and also put log normal is pretty close, but kind of doesn't fit as well. So this is also kind of fitted to the same sample here, but log normal the true distribution. relation between density of the extreme value distribution and the density of the log normal distribution. We see here that the density of the generalized extreme value distribution and log normal are here kind of pretty close. This first part here that we see has been kind of the part where they're here pretty close. At some point, it kind of really diverges, and the distribution, the density for the generalized extreme value distribution, kind of much higher than that of the log normal distribution. And that's kind of why we then see extreme events in these distributions, why we have kind of a heavy tail, so that we have a very acute distribution where we can still see large events which are rarely observed, but they still have some probability to occur. This is kind of way higher than the probability for the log normal distribution. We'll draw some random samples. That's we see those data sets that have these properties. Here, just kind of zoom in of both density functions. So we still see they're kind of rapidly decaying, both of them. But as said earlier, the GEV distribution is larger, so has a higher probability to draw any events on this kind of right-hand side of the tail of this distribution. The mathematical definition here, if we take n random variables, which are IID distributed, and then we define the maximum of those as the maximum mn, then we can use some mathematical background and theory and say kind of the probability that this maximum value is smaller than z is simply kind of the distribution function of this random variable to the power of n. So this is kind of the underlying observation or the kind of mathematical definition for an extreme value distribution here. And it turns out that there are only kind of 3 possible distributions that can hold this assumption. So whenever we think about an extreme value distribution that should have this property of being max stable, then we just have the viable distribution. Here's a simple example, the Gumbel distribution or the Fréchet distribution. So all of the 3 have different properties, different tail properties, and are kind of more or less useful for one or the other use case. And it even turns out you can kind of put them together in the generalized extreme value distribution. And then you have 3 parameters to kind of control them. And the shape parameter here decides whether this is part of the viable Gumbel or Fréchet distribution family of extreme value distributions. And well, location is kind of a mean value. Kind of you move the distributions along the x-axis, and scaling can kind of flatten or kind of make it more sharp or more edgy, the distribution at this case. So these are the 3 parameters that you can use. And kind of here's the mathematical equation, and here's kind of the corresponding functions in R. If you use the extreme value in R, then you get those distribution functions, and you can use them as usual. You have the density, the quanta function, and the force, the random number generator. So it's kind of the basic tool set in R if you want to kind of model. We have to, and also kind of so if we just kind of take a time series, it was temporal. Since data. Here's an example. These are the annual maximum sea levels in Venice, starting somewhere in 1887 or so. What first thing we observe and we kind of should deal with is there's some kind of trend in it. So it's about 0.35 here that this kind of annual maximum seems to increase on average. So if you really want to kind of model this in detail, then we would have to kind of deal with this linear trend and also kind of estimate if this kind of persists here. But neglecting this trend, we have already block maxima, so it's just kind of the maximum of every year. And well, unless we have some kind of slight side effects that this high tide event was kind of end of December and beginning of January, and this was kind of the strongest event over both years. These block maxima shouldn't be correlated in a sense, because they should be somehow spread over the years and be far away from each other in the sense of kind of temporal distance. And if we look at the histogram, we get this plot, and we see kind of there's one kind of outlier, one event here, one extreme event that you would like to kind of model and see kind of what kind of distributions can we use to describe this annual maximum sea levels in Venice at this case. You might layer easy and just use the built-in fitting function for generalized extreme value distributions. Methods is a point over thresholds method, where the idea is kind of, I have a time series, just have this picture here, kind of a time series that we see here, and based on this time series, I would like kind of to identify those extreme events that might be in there, and then I kind of just put a threshold, and everything above this threshold is considered to be extreme, and it's going to be modeled with an extreme value distribution function. And kind of first problem here, if we look into the series, it's very much correlated, these CO2 measurements. So we have to do something about that so that we kind of get somewhere closer. So this is typical autocorrelation plot. I guess most of you have seen it. So kind of working on lags that we have here and compare the correlation between those lag-wise observations. And we see kind of it's far beyond this blue line, which is kind of the significance value that we would like to kind of be below, more or less. So what we do is kind of a typical decomposition. So we have our observed values, we identify a trend, we identify a seasonal component, and we end up with some random noise on top. And now we're kind of interested, is there still some extreme outliers in this random noise? Is there any extreme values that we would have to